Hello, future elementary math teachers. Welcome to your pre-recorded lesson for Friday. In this lesson, I want to chat a little bit about properties of number sets, as well as take a quick look at how we can model basic addition and subtraction. And the idea here is if we can kind of figure out a couple really nice models to use concretely, we can use the concrete representations that we make to connect to the larger numbers where we're going to be involving some of the standard algorithms. So we want to be able to kind of tease apart what's happening inside the standard algorithms, and it's helpful to have some kind of concrete way to represent how addition and subtraction work. Before we get into talking about the two models for addition and subtraction, let's talk kind of more broadly about properties of number sets. So we're going to have a big old definition here, and we're going to essentially try to talk about a lot of the different properties and the words, the terminology that come up quite a bit. So how do I want to I'm just trying to think about how I want to organize this, because we're going to have a lot of like little subparts. Maybe I'll just organize it with numbers. So the first definition, we're going to say that a number set is closed. So a number set is closed under some given operation that we're talking about if we can take two numbers from the set perform the operation on those numbers and get a new result. So after I do this operation, I should get a new number. And what we want to do is check to see if the new number is also inside the original set. Okay, so this is the closure property under some kind of operation. So the big thing to note here is if I use the word closed, I'm going to also be talking about an operation. And in this particular lesson, we'll talk about addition and subtraction when we go to start working on some examples. So this is what we mean by closure. Pick any two numbers from the set, do the operation, and then we're going to see if the result is also a part of that original set. Okay, so that's one property. The next two properties kind of deal with brackets and how we're allowed to move numbers around. So we don't necessarily, do we need an operation? Yeah, we need an operation and we need a set to work with. So and the term that we want to define in this case is the term commutative. So commutative, kind of like you're commuting or driving to work. When it comes to mathematics, commutative is this idea that the order doesn't matter. Okay, so an operation is called commutative if I can take two numbers, and I shouldn't use addition here because it could be any operation. So an operation is called commutative if the order we perform the operation in doesn't matter. And again, once we kind of finish up our definitions here, we'll work on a couple examples of what this means. So some of our operations that we work with are super nice. They're always commutative. Some of the other operations we work with, the order is a little bit more important. And there's some results that come out of the fact that the order is important. So that's commutative. Let's talk about associativity. So we say an operation So an operation is called associative if I go to take three numbers, essentially, it doesn't really matter what order I combine two of the three numbers. So this is a harder one, I think, for me to write down in words. So give me a second to think about the best way to do this. Okay, so that's the best I can do via words. So let's kind of focus on trying to get some numerical examples to go along with these three particular definitions. 2 and 3 are going to feel kind of similar. They both deal with ordering, but commutative deals with actually changing the order of the numbers, whereas associativity, or the associative property, deals more with brackets, like almost like the order of the three things doesn't change, but how the order in which I combine the things might change. So let's take a look at some examples. And since our focus right now is just working with some of the basic counting numbers, the natural numbers, let's just work inside of that set for the time being. So the set of the numbers 1, 2, 3, 4, 5, etc., etc. So we're going to consider that as the set that we're working with, and we're going to consider our usual addition and subtraction operations. Now, when we think about the set of natural numbers, I can go into this set, I could grab any two of those numbers, I could add them together, and the result that I get is always going to be another counting kind of number. So, in other words, I could dive in, maybe pick my two favorite numbers, like the number 17 and, 34. Right? And I can add these things together, I get the number 51, and the result that we get is also inside of that set that we started with. So the idea is we pick two numbers inside the set, and they could technically be any two numbers. Then the second step is to perform the operation that's given to us. And then our last step is to check the result. So once I grab, any two random numbers, add them together, I get this result of 51, and we ask ourselves the question, is this number still inside of n? Now, in order for the set to be closed, this has to happen all the time. So I need to be able to go in, take any two starting numbers that I want, add them together, and still get an answer that's inside of the natural numbers. And it's true that this does happen all the time for addition. So, the smallest two numbers we could add together from the set are 1 plus 1. The result that we would get is 2. That's still inside of n. So we know that this set is closed under addition. The same is not true for subtraction. While I could go in, I could grab two numbers, subtract them, and get a number that still is inside of n. This doesn't happen all the time. certainly sometimes I could go in, I could grab a couple numbers, like maybe 5 and 3, and I could subtract them, and I could certainly get a number that's still inside of the counting numbers. That could happen. It doesn't always have to happen, though. So, for example, if we take the smaller number and subtract the larger number in this particular case, we end up getting -2. And -2 is not inside of n anymore. It's actually now an integer. Okay, so sometimes it works. Okay, but not all the time. So because it doesn't work all the time, we say that n, the set of natural numbers, is not closed under subtraction, because it's possible that I could subtract 2 counting numbers and I could get a negative number, and that's not inside of the set of natural numbers. Okay, so that's how we talk about closure. So addition's nice. Addition is essentially always closed inside of really every set. Subtraction, we have to be a little bit more careful. Subtraction's not going to be a closed kind of operation over the set of counting numbers. So just something to be mindful of if you're teaching those younger grades, right? To make sure that the order matters, right? We usually are going to take the larger number, subtract the smaller number for those first few years. Until we get introduced to, a thermometer, negative numbers, being able to go away from 0 in that left or downwards direction, right? It is possible to do this subtraction, but, sometimes we could get a negative kind of value. So hopefully that gives you an idea of what we mean by closure. We take our set that we're working with, in our case, natural numbers, and we take a look at whether or not we can add 2 and get something inside of n, or subtract 2 and get something inside of n. So addition, we're good. Subtraction, not always good. Okay, commutativity. Addition's always commutative. So it doesn't really matter what set we're working with. Addition is a really nice operation. So when we're thinking about or talking about commutativity, we mean the order. So if I were to start with 2 and add 3 to it, I know the result is going to be 5. But what happens when I switch the order? Do I still get 5 when I start with 3 and add 2 to it? Absolutely yes. Okay, so commutativity deals with the order of the 2 numbers. So is it possible to switch the order of these 2 numbers and still end up with the same final result? So that's the question, can I switch these and still get the same final answer? For addition, that's always true. It doesn't really matter what order these 2 numbers come in, I always get the same sum. However, when it comes to subtraction, subtraction is actually never commutative. In other words, the order in which we perform the subtraction is actually important. And so we saw this up top. So I'm going to take this exact example that we have up here of 5 minus 3 being equal to 2. But if I switch the order of these 2 numbers and do 3 minus 5, we get -2. So this is what we mean by something not being commutative. When I switch the order of the 2 numbers, the final difference that I get is going to be different. It's not the same. Okay, so this is why subtraction is not commutative, because switching the order of our numbers actually leads us to the opposite of what the first number was. 5 minus 3 is +2, Switching the order of 3 and 5 is going to give us the opposite of positive 2, which is negative 2. Okay, and this kind of lends itself to why subtraction and addition tend to have different names for talking about stuff. So if you are starting to, maybe do a little bit of reading online, you might start seeing some names of the different pieces of an addition sentence come up. So for example, when I'm talking about the two numbers as a part of this addition statement or addition sentence, both of these numbers are typically called addends. Right? 3 and 5 are both addends. And it doesn't really matter what order I put 3 and 5 in, I'm always going to call them addends because the order is not important. And of course, you've heard me say this number over here, this number here is called the sum of 3 and 5. Okay, so our final answer, sometimes you'll hear it called the sum. When it comes to subtraction, order is important. So each of these numbers over here actually has a different name attached to it. And I want to make sure that I'm going to give you the right names here. So that's addition. Yes, okay. I always know this one. This one's always called the difference. Right, the difference of 5 and 3. But our other two numbers are sometimes called the minuend and the subtrahend. And the reason the two numbers of a subtraction statement have different names is because the order that they come in actually is kind of important. So you probably haven't heard, maybe you've heard those, maybe you haven't heard them in a long time. But in case you're reading about subtraction statements and you're like, what the fuck's a minuend? It's the number that comes first inside of a subtraction sentence. And it has to be labeled differently than the subtrahend because the order that we show that subtraction statement is actually important, whereas it's a little less important for addition, so we just label those two numbers as the same thing. Okay, so that's a little aside about commutativity and kind of the problem of commutativity when it comes to subtraction. Last, let's talk a little bit about associativity. So for addition is nice. Addition is always associative. Okay, so our usual addition is super nice if I take any three numbers. Let's take 2, 3, and 7, and we start adding them together. Associativity is the ordering, but keeping the three numbers aligned in the same way. So in other words, when I see this statement, 2 plus 3 plus 7, I could tackle it in one of two ways. I could add 2 and 3 first, which would give us 5, and then add 5 plus 7 together to get 12. The other way that we could start a statement that looks like this, start simplifying this, is by starting with the number 3 and adding 7 to it. And if I start with the number 3 and add 7 to it, I'm going to get 2 plus 10, which is also equal to 12. So this is what we mean by associativity. Either we could start with the first two numbers, add them together, then add the third one, or we could kind of start in the middle and do that second addition first, and then add to it the first one. So addition is always associative. It doesn't really matter whether or not I add the first two numbers or add the second pair of numbers. I always get the same final answer. Okay, so it doesn't matter where I start my addition, my end result is always 12. Now this isn't true for subtraction, and in fact subtraction is never associative because it's not commutative. So we know that the order for a subtraction statement is important, so it makes sense that subtraction can't be associative, at least from my perspective. If the order matters for 2, the order is probably going to matter for 3. So let's kind of take a look at the two different ways we could start the following expression. So let's say we have 2 minus 3 minus 7. So there's kind of two ways we can do this. We could kind of start with 2 minus 3. 2 minus 3 would be negative 1. And then we could subtract 7 more, and that would get us to negative 8. Now, the other way we could kind of jump into this particular problem is to think about the second pair of numbers, which would be 3 minus 7, in which case we're going to get 2 minus negative 4. And 2 take away negative 4 is actually like 2 plus 4, which would be equal to 6. Okay, so the idea here is, the order that I subtract these numbers in is going to be important. Whether or not I start with the first 2 or start with the second 2, I get a different end result of either negative 8 or positive 6. So that's the idea with associativity. The way that I pair these numbers up and actually do the operation is important. So we get a different result. Okay, so that says different results of negative 8 or positive 6, depending on where your brackets are, right? Depending on where we start with this particular statement, simplifying the statement. So those are kind of your three big definitions, 3 big properties we will talk about quite a bit with all of our number sets. There's 2 more that kind of are very similar to each other, so let's talk a little bit about the last 2 things I want to define here as basic properties. And we'll just do this as a 1-2 kind of shot again. So let's talk about identity elements. Oh, what's the easiest way to... Do I want to say this generally? We might actually... It might be easier for us just to talk about additive identity. So rather than trying to make a general kind of case here, let's just talk about addition. And then when we get to multiplication, where the other important identity is, we'll talk about that. So the additive identity is 0. Okay, so 0 is what we call an identity element for addition only. Okay, so additive identity is the thing that we want to talk about here. And the additive identity is 0. This is because if I add 0 to anything, I end up getting itself. So here, little a represents any number, essentially. You can think about it as any whole number if you'd like. So the number 4 or the number 5. If I add 0 to it, I always get that number in return. So this is what we mean by an additive identity. It doesn't change the original starting number that we started with. Okay, so adding 0 to a number essentially results in no change to that number. So this is what we mean by an identity, and specifically the additive identity. We don't really talk about, 0 you could think about as the subtractive identity, because any number take away 0 is also itself. So 0 you can think about as the subtractive identity. I just really like saying that word. But we don't usually talk about the subtraction identity like that. We usually only talk about identities with regards to addition and with regards to multiplication. So I do want you to know that 0 is kind of an important number. It has this really nice special property over the addition operation. And the other one is in what we call numerical inverses. So okay, and what we're trying to define here or think about is what we call an additive inverse. And you can think about the additive inverse as like the opposite of the addition operation. It's like going to be the opposite number. So if I start with a number and I add b to it to get to 0, which is the identity element for addition, okay, so I start with a number, I add something to it to get to 0, then we say that b is the additive inverse of what we started with. So, for example, let's say we start with the number 4. What number would I have to add to it in order to get to 0? If I can find that number, it's called the additive inverse. Now this number, you probably know what it is. It's not inside the set of natural numbers. It's actually an integer. And in fact, it's -4, right? So -4 is called the additive inverse of +4. So it's just some terminology that you might see kind of crop up as you're doing some reading. Essentially, the additive inverse, we think about it as like the additive opposite of the thing that we're working with. So -4 is the addition inverse for +4. Okay, so our positive and negative numbers have a really nice relationship between them. They're related to each other by not only being opposites, but if we were to add them up together, we know that we should return back to the number 0. Okay, so those are kind of the big operations I think that are important for us to know with regards to addition and subtraction. Of course, if you have any questions along the way, just make sure you kind of jot down those questions, and we can talk about those questions when we get together on Monday. What I want to do for the last little bit of the class is just give you a couple models that are helpful for addition and subtraction, so that we can essentially try to figure out how some of our original algorithms work for these operations. So let's go models for addition and subtraction. So when it comes to addition, addition is quite simple and straightforward. Subtraction tends to be a little bit harder, and we sometimes tend to think about subtraction in terms of addition, and we'll talk about that when we get there. So, I mean, for addition, all you really do is think about like cardinality numbers. And the easiest way to think about this is, we have a group of objects that has a certain number of things in it. We're just going to combine that with a different set of objects that also has a certain number of things in it. And to be honest, that's the easiest way to really visualize addition. So if I wanted to think about how do I model something like 3 plus 4 is equal to 7, well, I might start with a group of 3 objects. Maybe they're pennies, maybe they're quarters, maybe they're pencils, maybe they're erasers. I don't really know. But I have a group of 3 objects over here. I got a group of 4 objects over here. They may or may not be the same things. They could be erasers, they could whatever. It could be people. And then all we do is just kind of combine all of these things together into one region, and we add up all the things. So that's the easiest way to think about addition. I think that's a very straightforward way to think about addition. It's a very intuitive and natural way to think about addition. When we start working with manipulatives, and specifically base 10 blocks, just something to kind of keep in mind here is that as we're combining some of these things together, we may have to go through the regrouping step if we notice that we have 10 of a similar kind of base 10 block. Okay, so we can use regrouping if we're modeling with base 10 blocks. So in other words, if I have, I'm combining some stuff and all of a sudden I look at my ones after I've combined my singular units and I notice I have like 12 units. Well, it kind of makes sense to regroup 10 of those into a 10 rod and then look at, maybe the 10 rods. Do they need to be simplified down? So it's just something to be mindful of as we kind of work into the standard algorithm. We will tend to use this idea of regrouping quite a bit with regards to addition. Okay, let's talk about the fun one. I actually really like thinking about subtraction and thinking about ways to model subtraction. So there's kind of I would say two major ways to think about subtraction. The first one we don't use with regards to thinking about the algorithm for subtraction, in my opinion. But it is helpful for some of these kind of smaller cases because addition's a little bit more intuitive than subtraction. So this is called the missing Addend model. And sometimes I've also seen it referred to as counting up. So the idea here is if I have some kind of subtraction statement like this, 10 take away 3 is equal to what? What we actually do is reframe this question into an addition. So in other words, there's a relationship between the subtraction numbers we have here, 10, 3, and question mark, and a similar question in addition. So 10 take away 3 is equal to what is actually kind of the same thing as saying start with 3 objects, add some stuff to it until you get to the number 10. So this is the connection between a subtraction statement and the kind of similar addition statement. And this is what we mean by missing addend. So we think about that number that we're looking for. This is called the missing addend. And if we could find this number, that would solve the problem. And we know, for example, just using our fingers, if I start with the number 3, now I can count up to 10. Okay, I know 10 looks like this, so I have to count up 1, 2, 3, 4, 5, 6, 7. So that's the idea here. If I can reframe subtraction into an addition problem, then it becomes trying to count up until I get to 10, essentially. Now this is nice for working with counting numbers and small kinds of counting numbers like this. It's nice when we're working with money as well. Essentially, it's nice when we're working in situations where it's easy to count up to something. It's hard to use the missing addend model or the counting up model in personal opinion when working with integer numbers, right? So if I all of a sudden maybe change this question to 3 take away 10 is equal to what? It becomes a harder question, I think, to think about as a counting up kind of problem. So just be mindful of that. It's nice, in the younger grades when we're working with all kind of positive counting numbers and not working with integers yet. It's really nice with money when we're trying to make change with money, for example. It's a nice way to instead of work with subtraction, think about addition, because I find addition a little bit more intuitive. So just a couple of things to kind of keep in mind. There are some drawbacks, I think, to this model, but it does lend itself really nicely to the younger grades. Now, the model that I typically like is the takeaway model. And the takeaway model would look something like this. So if I want to model something like 10 takeaway 3 is equal to 7, I'm going to first model the minuend. Okay, so for example, we have 10 here. So let's just put 10 dots here to represent the minuend. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so we model our minuend. There are 10 objects. Okay, the second thing is to circle the subtrahend. Okay, so in red, I'm going to just grab 3 objects like this. So I'm going to circle 3 objects. It could be any 3, like I could have circled it over here. It doesn't really matter. But I'm just going to grab 3 of these things and circle them. Okay, and then what we're going to do is we're actually going to take away those 3 things. So the last step here is to take away those things. Okay, so this is why it's called the takeaway model, I guess. And then your result should be what's left over. So 1, 2, 3, 4, 5, 6, 7, right? And sometimes you'll see me draw like a little arrow like this. If you see me circling something and drawing an arrow, it means I'm going to be taking away those things. I'm moving those objects away from the actual picture that I'm working with. And then whatever's left over is our result. Now, I want to just make a little note here as well. When using the takeaway model, sometimes you don't have enough. Sorry, I should be very careful. When using the takeaway model with base 10 blocks, you sometimes don't have enough blocks to actually take away. So when we start to work on the algorithm like we're going to do on Monday, we just have to be mindful that sometimes we need to break apart a larger block in order to ensure that we have enough smaller blocks to actually take away. So with simple statements like this, 10 minus 3 equals to 7, very easy to model this takeaway process visually, concretely. Working with larger numbers in subtraction, it gets a little trickier. So when we're modeling, with base 10 blocks, may need to regroup in order to ensure that we have enough blocks to actually take away. Okay, and we'll take a look on Monday where that happens. That usually happens when we're going through what you guys might know as like a borrowing step. So I'll just look at, maybe a small example like this, right? If I actually want to go through the algorithm to do 20 take away 13, what we usually do is kind of look at this first column and we go, okay, well, 20 is just 2 rods. But I don't have enough units to be able to take away 3 units. So we would normally go through this kind of borrowing step, where we kind of break down one of these larger base 10 blocks into smaller base 10 blocks, and then now we have the capacity, now that we have 10 units, to be able to take 3 of them away. Of course, it seems kind of silly to use the standard algorithm on something like this when we could use the missing addend or counting up model. I know that 13 plus 7 is equal to 20, so it doesn't really make sense to use the algorithm there, but hopefully that gives you at least kind of a smaller idea of where it makes sense to regroup, but in the opposite direction. So I'm just going to take a quick little peek. I think that's everything that I wanted to cover for the class today. And then what we're going to do in class on Monday is we will take a look at these standard algorithms for addition and subtraction and start kind of working on how we can model those things and make sense of those operations. So that's where we're at. For next week, it's going to be a lot of addition and subtraction on Monday and Wednesday, and then we'll start to kind of work our way into multiplication, I think, by next week on Friday. Okay, so have a lovely weekend, guys, and I will see you all on Monday.